Hello, and welcome to Chapter 9, Section 1. In this chapter, we start talking about hypothesis testing, or hypothesis tests. It's also called significance tests. There's either name works, interchangeable. So last chapter, we talked about confidence intervals and how we were trying to use a sample to estimate a population proportion or a mean based off of that sample. So we came up with a range of numbers that were like, okay, we think the population mean or proportion is going to be around these numbers. So in this chapter with the hypothesis test, what we're actually trying to do now is still looking at a sample. We're trying to see whatever mean, proportion, whatever we get from that. We're trying to see, does that actually make sense to what we claimed? Because that was a question we were trying to answer last section as well, where we were looking at, like, when we made our confidence interval, did the number we were being asked about, was that included in that confidence interval? So it's a similar process here, just we're going to be using probabilities instead of a confidence interval to make that decision for us. So the reason it's called a hypothesis test is that we're going to use this procedure to make a decision. So is the claim true or not? We're making that decision between two competing claims. The claims themselves, we call them hypotheses. So we have two different hypotheses that we're going to be looking at and then trying to decide if one of them is true or not. So first, I want to talk more about these hypotheses. There are two, like we said. And so also I wanted to make sure you knew hypotheses is the plural of hypothesis. Just putting that out there. All right, so the first one is named the null hypothesis, and we abbreviate it using H for hypotheses, and then like subscript O. So the O we kind of read as H naught, and sometimes you'll hear that. Sometimes you'll just refer to it as HO. Either way, we know it's supposed to mean the null hypothesis. The null hypothesis is kind of like saying, like, there's no difference in the claim. So whatever number we're claiming, or like, whatever is claimed in the problem, this would be your null hypothesis. A lot of times the claim itself will use the symbol equals in there, and I'll show you some examples of hypotheses so that you can see how this is used. The second hypothesis is the alternative hypothesis. So this is supposed to be the opposite of the null hypothesis because we said there's supposed to be competing claims, meaning they're opposites of each other. So the alternative hypothesis is what we actually believe, and this is kind of based on the questions in the problem. So that's how we'll use the alternative hypothesis to state what we believe. And in these hypotheses, we will use symbols like the less than sign, the greater than sign, or the does not equal sign. So real quick example on how to write a set of hypotheses. So let's pretend we're playing this game where we have to flip a coin. If it lands on heads, then we win $5, cool. But if it lands on tails, then we have to end up paying $3. All right, but then we end up losing $15 in a row. So I've played 5 times, lost 5 times. And I think we've been conned. Is there any convincing evidence that this coin is weighted to land on tails more than heads? So if we're trying to answer this question with a significance test or a hypothesis test, we'd first have to write down our hypotheses. So if we're talking about landing on tails more than heads, it's mostly going to be like a proportion. So the percent of times that we land on tails versus heads. So I'm going to let P, the proportion, be the true proportion, so like overall true proportion of landing on tails. Because remember, we're always using a sample to then generalize to a population. So when we make our hypotheses, we always want to use symbols that stand for populations, never samples. So if you remember our proportions for a sample, we would use P with a little hat on top. So we would never use P hat in our hypotheses. Same thing with means, we would never use X bar. In our hypotheses, we would always use mu. So this is where the difference in notation, the symbols that we use, really matter. So the next part of our hypotheses that I want to talk about is the number itself. So we're believing, like, we think that this coin is weighted because we've just lost a whole bunch. So if it's weighted, that means it's not like 50-50 when we flip this coin. So 50-50 meaning like 50%. So that's why I'm using 50.50 as my proportion. The symbols here, so in our null hypothesis, we always assume that there's no difference in the claim. So it's always going to be an equal sign in there. So our null hypothesis, we're basically believing that the coin is actually fair. It's going to flip 50-50 for heads and tails. But then what we actually believe, or based on the question, is there convincing evidence that this coin is weighted to land on tails more? Then if P is going to stand for me the number of times, the proportion of times we land on tails, then tails would have to be a greater percentage, so over 50%. So that's why we use this greater than symbol. So in general, every time we write hypotheses, the numbers for both hypotheses have to be the same because remember they're competing claims. So they have to be the same number, just different symbols. Our null hypothesis, the rule is basically to always use an equal sign. So that's kind of nice. You don't really have to think about it. It's just the alternative hypothesis where you need to figure out which symbol to use, the greater than, less than, or does not equal. And again, the way to tell is from the question part of the problem. And lastly, always use symbols that stand for population parameters, not sample statistics. So P and mu versus X bar and P hat. The next part of a hypothesis test I want to talk about is the assumptions/conditions. So these are similar to what we did when we made confidence intervals. Because the entire process of a hypothesis test or making a confidence interval is all based on a normal curve and knowing that your sample was well chosen, in order to then generalize to the population, we need to make sure these things are all part of our process. So the first thing we are looking for, just like in our confidence intervals, is the random independent samples. So we need both of those things because remember the random part, we need to make sure that our sample was actually well chosen. Our independent samples make sure that that standard error formula that we had actually works. And then we need normality because we are using the normal curve or even the t-distribution to then calculate probabilities or to find a critical value. So that's why we need all those things here. So in this example, I'm just going to continue with this whole coin flip thing. So random independent samples is kind of weird when we're talking about coin flips because it's not like you can like take a random sample of coin flips. So that's kind of weird. So that's why this is like both assumptions and conditions because we're going to assume some things. So we can say something like we can assume that flipping a coin is considered random and one coin flip wouldn't affect the next, thus independent. So here we're assuming randomness because there's not really a way you can randomly flip a coin. And then we have independence because your coin flips aren't going to affect each other, so they're not dependent events. And finally, normality, this is the same checks that we did for our confidence intervals. So if you're dealing with proportions, you're going to use the large counts condition. If you're dealing with means, then you have the CLT, the central limit theorem, or if you know the original problem is already normally distributed, or if they give you a set of data, then you have to make your graph. And then with that graph, you're looking for extreme skew. So as long as it's not extreme skew and there's no outliers, then we can consider this approximately normal. The next part of a hypothesis test process that I want to talk about is the p-value. So p-value is just a probability. We talked about we are using a hypothesis test to make a decision using probabilities. So here's where we actually calculate the probability. And our probabilities are based off of the normal curve. So the interpretation for a p-value sounds something like this, and it kind of defines what it is. We are assuming that the null hypothesis is true. So remember, the null hypothesis is the one where we're saying the number is what the claim is. The probability that the statistic from the sample, so whatever we got from our sample mean or sample proportion, would take a value as extreme or more extreme than the one observed is whatever the probability is. And the wording is kind of weird. So to me, it makes the most sense in a visual format. So if we think about a normal curve or a t-distribution where it's kind of almost normal, we would put the population parameter in the middle because that would count as our mean, either the proportion or the population mean, and that would go right in the middle. Then we would calculate our standard error for the standard deviation of our normal curve. So those were our two formulas based on whether we had proportions or means. And then, so what we're saying here with the taking on a value as extreme or more extreme than the one observed is the one observed that we're talking about is the one we got from our sample. So the sample mean or the sample proportion. So I'll use the symbols x bar or p hat because those are the symbols we use from samples. So let's say we got that number in our sample. That's what happened, and we're trying to compare it with the mean of the population. So this mean of the population is basically saying like our null hypothesis. If we are assuming that the null hypothesis is true, then the population mean or proportion should be right in the middle. And so we are calculating the probability that whatever we got, the one we observed, is as extreme or more extreme. It talks about like shading to the outside of the normal curve. So assuming we got a mean or proportion that was like to the right of our population mean or proportion, then we would shade to the right. If we got a number on this side, we would shade to the left. So always away from the mean is the direction that we're shading. But that's this whole extreme or more extreme than the one observed. So the p-value just talks about that probability right there. We're just using the normal curve to calculate probabilities like we've done for ages. So with this probability, we're trying to use that to make our decision. Does the null hypothesis seem accurate or is it false? So once we calculate that probability, what this means is that if we get a p-value or the probability that we calculate to be very small, small probabilities mean that event shouldn't have really happened. It's like supposed to be really rare. So whatever we got from our sample, the mean or the proportion from that sample that we actually got should not have really occurred because it's such a rare event. But when we took our sample, we actually got that number. So if we actually got it and it's supposed to not really ever happen, then this means what we assumed originally, that the null hypothesis was true, should not be true then. Because if we're getting something from our sample that's not supposed to happen, then whatever we assume to get that to begin with shouldn't be right. So at this point, if your p-value is very small, this is actually good. This is that convincing evidence that they are asking about in the original question. Because if you remember, we are looking for, is there convincing evidence that this coin is weighted? So a lot of times they'll use the words convincing evidence to be like, okay, our probability is we're looking for a small probability to be that convincing evidence. So I want to go back to our picture right here really quick because right now we've shaded like if our mean was greater than whatever number. And we also talked about you can shade if you got a sample proportion or mean that was less than, then you would be shading to the left. So in our alternative hypothesis, this would be when you use greater than as your symbol, less than as your symbol when you shade to the left. And we also said there was one more where it was the does not equal to symbol. So when that happens, we're actually finding both sides because we're saying we don't care if it's greater than or less than as long as it does not equal that number. So sometimes you'll see this written as a two-sided test, because when we're calculating the probabilities, we are calculating both sides of it rather than shading just the right or just the left. So anytime it does not equal, you're going to be using both those sides probabilities there. And again, it's called a two-sided test. In the question, because we're using the question part of our problem to decide which of those symbols that we use, the question for a does not equal a two-sided test would sound something like this. Is there convincing evidence that this coin is weighted? Just weighted at all. Where we're not specifying whether we land on tails more than heads, so it might be weighted in either direction, and we don't care. We just want to know, is the coin weighted? So if that's the case, then that would be a two-sided test where we would find the probabilities of both sides. So next I want to talk about when our hypothesis test is considered statistically significant. So we've talked about this phrasing before, where we were trying to see if our results were statistically significant. Again, to review, our definition of statistically significant is that it's not likely to happen just by chance. So if we think back to our coin flipping scenario, if we got like 5 tails in a row, then did that happen just by chance, or is that an actual weighted coin that we're dealing with, and so that's why we got that? So statistically significant would occur if we got that p-value, calculated that p-value, and it's a really small number. So again, really small numbers, really small p-value means that the numbers that we got in our sample shouldn't really have happened, so that means our null hypothesis can't be true then. So that when we have to say that the null hypothesis is not true, that counts as statistically significant, because we're basically proving that our alternative hypothesis then is correct if we're saying no, the null hypothesis cannot be true. So if we're looking for a small p-value, then we actually need like a rule for how to tell when the p-value is actually considered small. So we use something called the significance level, and we use the symbol alpha to describe our significance level. So as long as our p-value is less than our alpha, then that means our p-value is actually small enough. We have more evidence against our null hypothesis, because remember we're saying small p-value means our null hypothesis cannot be true. So if the null hypothesis cannot be true, then that means our alternative hypothesis then is good. We have more evidence to support it. So our alpha level, our significance level, has to do with our confidence levels. So if you remember our confidence intervals in last chapter, our most common confidence levels were 99%, 95%, and 90%. So alpha, the significance level, is directly related to that. For 99% confidence, that means alpha would correlate with a 0.01 significance level. So this means in order for us to actually be able to make a decision about our null hypothesis, our p-value has to be smaller than 1%, which is a really small probability. And so that's where you get the most confidence from it. So 99% confidence means that we can like have full support of our alternative hypothesis with 99% confidence because our p-value is so small. And then for a 95% confidence, the significance level would just be 0.05. So now we're just looking for a p-value, a probability of less than 0.05, and so on. 90% would correlate with a alpha, or correspond with an alpha level of 0.10. So as you go down in confidence, the alpha level also increases, so that you have like more chances of being able to support your alternative hypothesis versus your null hypothesis. Alright, so once we've decided whether our p-value was less than or greater than alpha, our significance level, then we can decide what do we know about our null hypothesis. If our p-value was real small, less than alpha, then we would reject HO. When we reject HO, we're basically saying our alternative hypothesis, the HA, is true, because we said no to HO, HA must be true. But let's say our p-value was big. That means we have to fail to reject HO. We can never, ever accept HO, because accepting it is basically saying, oh, HO has to be true. But this is not what we've proven. So we've only proven, or we haven't proven that HO is true, so that's why we can't accept it. Because if you remember, HO is the one where it's like, the mu is equal to whatever number, or the proportion is equal to whatever number. We haven't actually proven that that is the actual number. It just means that that number is not false. It might be. So this is similar to when we made confidence intervals, and the number that we were being asked about was actually included in the interval. Remember, that meant that it was inconclusive, because in our interval, if the number was included, that means numbers around it, less than or greater than, were also included. So we didn't actually know if the claim was actually true or not. It was inconclusive. So this is the same thing here. If our p-value is too big, then we just fail to reject HO. We can't say for sure whether it's true or not. Alright, the last thing I want to talk about in this video is the types of errors that we could make. Because we are making decisions, what if we mess up? So there's two types that we talk about. The people who made these, or who defined these, were not real creative with their name making. We have type 1 error or type 2 error. So not real creative there, but it's easy to remember. So for type 1 error, this occurs when you reject HO when you shouldn't. So our null hypothesis got rejected because our p-value was small, but we actually don't have enough evidence against it. So this would occur when, we calculated something wrong, like when we took our sample, it was a bad sample to begin with or whatever, and so whatever we got from that sample, that number shouldn't really have occurred in the first place, and so we made an error. That's a type 1 error, when you end up rejecting HO when you shouldn't. Type 2 error is when you fail to reject HO when you shouldn't. So using the context of the example that we were using at the beginning of this section, the type 1 and type 2 error, this is what it would look like based on our hypotheses that we made back at the beginning. So we said our null hypothesis was that P equals 0.5, meaning the coin was not weighted, that it's fair. So type 1 error would sound like this. We would reject our null hypothesis so that we think our P equals 0.5 is actually false because we rejected it. And so we think the coin is weighted because it's not fair. But this was a mistake because it was a type 1 error. So then we would end up wrongly accusing the game of being rigged. All right, type 2 error would sound something like this. We would fail to reject our HO. So we think that the probability that landing on tails is actually greater than 0.5 is false. So if we fail to reject HO, notice how I didn't say that P equals 0.5 is true because we don't know that the null hypothesis is true. We just know our alternative hypothesis is false. So we don't think that this game is rigged. The coin seems like it's fair. So we lose our $15, but this was a mistake. So we could have asked for our money back. I don't know if you actually would, but since the game was actually rigged. And so based on these two types of errors, it kind of sounds like type 2 was worse because you would end up losing your $15 without any recourse for trying to get that back. But type 1, you're just wrongly accusing someone of something, and I don't know if you think that's good or bad, but still, that's kind of what type 1, type 2 errors would sound like. We don't actually go into like how the type 1, type 2 errors are made. Basically, it's from like taking your samples incorrectly. But we do need to know what the consequences of making each type of error would look like. And so this is something that you need to be able to explain using your words when we do problems and such. Alrighty, that's it for this section. Thank you for watching, and we will go into how to actually perform the entire hypothesis test in our next 2 sections. Thanks for watching. Don't forget to like and subscribe. Bye.